at the subtraction of vectors now. When we subtract a second vector from a first vector, we can effectively add a vector with the same magnitude as that second vector, but the opposite direction to the first vector. So what does that mean? Let's consider this example. If we had the vectors a and b as shown, we know that to add a and b, we just have to draw them head to tail, and we end up with our resultant vector a plus b. If we want to work out what a minus b is, we can consider our vector a and the vector minus b. So the vector minus b has the same magnitude as b, but it is pointing in the opposite direction. So to work out a minus b, we then add our vectors a and minus b, and you can see the resultant that we get here. Now, a context in which you'll often come across the subtraction of vectors is when we're looking for the change in something. When we're writing this as an equation, we use the capital Greek letter delta to represent the change. So, for example, if we're considering the change in the velocity of an object, we can write, well, the change in velocity is equal to the final velocity minus the initial velocity. So let's have a look at an example of using this equation now. So our example is, a car is going at 60 kilometers per hour south. It then passes through an intersection and is traveling at 80 kilometers per hour east. What is the change in velocity of the car? Okay, so we know that the change in velocity of the car is equal to the final velocity minus the initial velocity. So the final velocity we're told is 80 kilometers per hour east. So let's draw a vector to represent this. This is 80 kilometers per hour, and we've drawn it going east if we take this as north, east, southwest. And minus the initial velocity, initially it was traveling at 60 kilometers per hour south. So this is 60 kilometers per hour. So now what we're going to want to do is add a vector pointing in the opposite direction to this one. So we can do this as 80 kilometers per hour this way plus 60 kilometers per hour in the northerly direction, so in the opposite direction. So now we've got two vectors that we need to add together, so we can just do that with our diagram. We've got 80 kilometers per hour here, and then head to tail we've got 60 kilometers per hour here, and so our resultant vector is going to be this vector here. So we're going to want to work out this angle and the magnitude of this vector. Because this is a right angle triangle, we can use Pythagoras to get the magnitude. So we've got 80 squared plus 60 squared, which we're taking the square root of. When we take the square root of this on the calculator, we get 100 kilometers per hour. So that just leaves us this angle here to work out. So with this angle, we've got the opposite side and the adjacent side. So we can use tan theta is equal to opposite, which is 60, over adjacent, which is 80. So this tells us that theta is equal to the inverse tan of 60 on 80, which is equal to 37 degrees. Now, to give this angle as a bearing, we take this as north, and we'd want to know the angle it makes with north, which is that angle in there. So if we call that phi, then we can write, well, phi is equal to 90 minus 37. That's because this angle here is 90 and we're subtracting off the theta. So doing that, we end up with 53 degrees. So this tells us that our delta V is 100 kilometers per hour, and it is in the direction north, 53 degrees east.